The F-1 for Tomcat was engineered with a singular purpose: to intercept Soviet supersonic bombers before they could launch long-range missiles threatening the U.S. Navy's aircraft carriers. At the time, no aircraft in the U.S. military's arsenal could counter this threat effectively. A new breed of fighter was required, one capable of reaching Mach 2 to chase down high-flying bombers, agile enough to dogfight their fighter escorts at slower speeds, robust enough to endure the punishing landings on carrier decks, and equipped with the most advanced air-to-air weapons ever developed. Additionally, it needed a radar powerful enough to guide those weapons over a distance equivalent to New York to Boston. To meet these demands, the F-1 had to be a shapeshifter, adapting instantly to the battlefield's needs. Its variable sweep wings allowed it to excel into roles, high-speed interception and close-quarters dogfighting. This is the story of the F-14 Tomcat's remarkable engineering. Variable sweep wings were not a novel concept when the F-1 was proposed. During World War II, German engineers theorized the advantages of a plane that could adjust its wing angle mid-flight. Despite the design's complexity, they pursued a prototype as part of the emergency fighter program, a desperate effort to counter the Allied air campaigns crippling the Luftwaffe in 1944. The Messerschmitt P1101, a secretive project, was never completed. As U.S. forces advanced toward Berlin in the war's final days, they discovered this innovative machine. Recognizing its potential, the design was shipped to the Bell factory in Buffalo, New York. 6 years later, the Bell X-5 emerged, bearing a striking resemblance to the German prototype. However, the X-5 was flawed, and it would take decades of advancements in materials science and aerodynamics to make variable sweep wings practical for combat aircraft. Variable sweep wings allow a plane to adapt its aerodynamics dynamically. At slower, subsonic speeds, a lower sweep angle generates more lift with less drag, ideal for loitering to protect multi-billion-dollar aircraft carriers. When speed is critical, the F-14 could sweep its wings back to achieve Mach 2.3, a capability rarely included due to added weight and maintenance costs. To make this feasible, Grumman, the F-14's manufacturer, prioritized weight reduction, starting with the wing box, the structural core connecting the wings, resisting bending forces, and supporting the aircraft's weight through its fuselage connection. The F-1 was a heavyweight, the most expensive fighter the U.S. had ever developed. It carried two massive engines capable of propelling it to twice the speed of sound, 6 advanced air-to-air missiles exclusive to the F-14, 7 tons of fuel, a complex swing-wing mechanism, and a radar unmatched in power until the F-22's introduction. To keep the wing box both strong and lightweight, Grumman chose titanium, a material known for its strength-to-weight ratio, but notoriously difficult and costly to work with. To handle titanium, Grumman built a unique manufacturing facility, using electron beam welding, a process that bombards metal with high-speed electrons to generate heat in a vacuum, preventing oxygen contamination that weakens titanium welds. This technique produced a wing box 15% lighter than an aluminum equivalent, a masterpiece of structural engineering that avoided the 50% weight penalty of bolted titanium connections. With this lightweight foundation, Grumman could add the F-14's heavy components, starting with its engines. To reach Mach 2.3, the F-1 required powerful engines with afterburners capable of operating across subsonic, transonic, and supersonic flight regimes. Jet engines need subsonic air entering their compressors, so as the plane approaches supersonic speeds, the engine inlets must slow the airflow. Learning from the F-14's predecessor, the F-111, Grumman avoided curved inlets mounted on the fuselage, opting for simple box-shaped inlets to simplify aerodynamic analysis and ensure high-quality airflow. These inlets featured a fixed ramp at a 3-degree angle, followed by 3 computer-controlled compression ramps adjusting 40 times per second based on Mach number. At subsonic speeds, the ramps remained open, even overcollapsing during takeoff and landing to maximize airflow. At Mach 0.8, the throat area narrowed, reducing to 60% of its maximum at Mach 2, positioning shock waves to slow supersonic airflow to subsonic speeds. A bleed air door removed slow-moving boundary layer air, exhausting it over the wing's upper surface. This oversized inlet, 10% larger than needed for the original engines, allowed future engine upgrades by adjusting the bleed door, showcasing remarkable foresight. The F-14's initial engines, however, were problematic. The TF-30, inherited from the F-111 and F-4D, was the world's first turbofan with an afterburner, suitable for bombers but ill-suited for the F-14's aerobatic demands. The TF-30 was prone to compressor stalls, where maneuvers disrupted airflow, causing the compressor to lose power or flame out. This issue led to tragic accidents, including the death of Kara Holtgreen, the first female fighter pilot killed in U.S. military history, when a compressor stall during a carrier landing caused a deadly roll. The F-14's engine placement, far from the centerline, exacerbated asymmetric thrust issues, sometimes leading to flat spins, as depicted in Top Gun. In 1984, the Navy began upgrading to the F-110 engine, designed for fighters with inlet guide vanes to prevent stalls. The F-110 offered 32% more thrust, eliminating the need for afterburners on takeoff, reducing fuel consumption, and extending flight time by 34%. Smaller and lighter, with fewer compression stages, the F-110 was a significant improvement, distinguishable by its distinct nozzle design. The F-14's weaponry was equally groundbreaking. It could carry up to 6 Phoenix missiles, the most advanced air-to-air weapons of their time, designed to counter supersonic bombers. These missiles, paired with the AWG-9 radar's 10.2 kilowatt output, could engage targets at unprecedented ranges, tracking 24 targets and guiding all 6 missiles simultaneously in track and scan mode. The Phoenix accelerated to Mach 5, climbing into the stratosphere with a 3-minute burn time, switching to its own radar within 18 kilometers for terminal guidance. Its tail-mounted control surfaces enabled 17 grams turns, outmaneuvering any bomber. However, the missile was rarely used outside testing, as the Cold War scenario it was designed for never materialized. Carrying 6 Phoenixes also exceeded carrier landing weight limits, risking the jettisoning of a $1.3 million weapon. Landing on a carrier was a high-stakes operation. The F-14's arresting hook had to catch hydraulic arresting wires to stop the heavy aircraft over a short distance. A 2002 incident highlighted the hook's vulnerability when it broke due to hydrogen embrittlement from improper refurbishment. Takeoff was equally intense, with the pilot kneeling the plane to compress the nose gear, lowering the launch bar to connect to the carrier's catapult shuttle. Powered by steam or electromagnetic systems, these catapults accelerated the F-14 to 180 miles per hour into seconds, with the compressed nose gear aiding a safe nose-up moment on release. The F-14's swing wings, controlled by the flight computer, varied from 20 degrees for takeoff and landing to 68 degrees at Mach 0.9, with a 78-degree setting for compact storage. This adaptability optimized the lift-to-drag ratio, critical for dogfights and transonic flight. At low speeds, straight wings maximized chordwise airflow for lift, essential for carrier landings. As speed increased, sweeping the wings converted airflow to spanwise, reducing drag and delaying supersonic shock waves. The wing pivot, supported by a titanium wing box, handled immense forces, aided by the fuselage's lifting body, which increased the total lifting area to 93 square meters, reducing stress on the wings. The F-14's control surfaces were unconventional, using spoilers for roll at low speeds and a boron fiber composite tailer-on at higher speeds. Boron fibers, stronger but costlier than modern carbon fibers, were used due to the era's material limitations. To address aerodynamic challenges, inflatable canvas bags maintained a smooth contour behind the retracted wings, and extendable glove vanes countered the rearward shift of lift at supersonic speeds, enabling 7.5 grams. However, these vanes were often disabled or removed due to maintenance demands and the absence of the high-speed scenarios they were designed for. The F-14 was retired in 2006 after 32 years, as the Soviet threat waned and versatile stealth fighters like the F-35 emerged. Its high maintenance 30 to 60 hours per flight hour made it unsustainable. Yet, its specialized design remains a marvel of engineering, blending speed, agility, and firepower to protect the Navy's fleet.